Welcome to lecture 6. Today we're going to talk about bias and variance. So you're going to see a really canonical trade-off in machine learning between bias and variance, bias squared and variance. That's going to lead us into some discussions about regularization, model selection, and some other things there. In particular, when we start to go through this, you're going to see some stuff that I hope is actually quite useful when you do machine learning in practice. So we'll first talk about this kind of fundamental tension in models, which are overfitting and underfitting. So you'll go through this, we'll motivate exactly what those two concepts mean. And then I'm going to try and give you a modern twist on that a little bit later. Overfitting and underfitting are naturally going to lead into bias and variance. So once we have kind of the picture version of how overfitting and underfitting work, we'll do the mathematical version. And that will be the bias variance trade-off that is very famous. It's one of those things you hear about for machine learning. And then that will motivate a particular technique, regularization, or it's really a class of techniques, to reduce the variance for the models. And we'll see why that's so critical. And then I couldn't help myself. There are two places I put in kind of a modern twist that I think are helpful. One is I'm going to tell you about two fairly recent-ish papers, which are called double descent, which is how bias variance, the classical way I'm going to teach you for the first part of the lecture, how it deals with modern models, which I think is really interesting to know. And you should just be at least aware that it exists. This is something that people are working on quite a bit. And we'll also talk about this very cool paper. I was actually talking with one of the senior authors this morning, which is called ImageNet to ImageNet V2, which talks a little bit about another form of overfitting that you could worry about, which is called adaptive overfitting, and why that actually hasn't been a problem in models. So I really want to share those with you because I think they're pretty interesting lessons about, where machine learning is going, right? We'll talk about model and parameter selection, train, dev, and test splits. We'll talk about a very classical method from stats, which is called k-fold cross-validation. You may have seen this method before. We'll be able to analyze it quite cleanly. And then we'll talk about this compute-efficient algorithm called hyperband, which is an algorithm I love. It's by some friends. One is at CMU now, one's at Washington. And it's a very compute-efficient way to fit parameters, to tune hyperparameters. And it's just very simple and clean. It has 4-slide animation, and you get the idea. And it's actually really useful. And actually has nice theory underneath the covers. We won't do that here as well. But that's a good way to actually tune parameters in a bunch of places. So today we're really wrestling with this really central question in machine learning. Given a finite noisy sample, how do we pick a model that will generalize? And this is the key question in machine learning. This is what motivated both statistical theory and what we do now. We're going to train a model on some train set. We're going to apply it on some test set. And we'd like to have some procedure that on that training set guarantees, to the extent possible, that we behave on that form on future data sets. Okay? So this is the critical question in machine learning. We're going to talk about it. Okay, so let's get some pictures about overfitting versus underfitting and hopefully make this concept, crystal clear in your head. All right, so here's the setup. There exists some true function in the world. We don't get to see those functions, right, that are there. But this true function, which I've drawn here for illustration, is this function h of theta, which is going to be some quadratic. Okay. Now, it's weighted by some parameters, theta 2, theta 1, and theta 0, and it generates the real world. Okay, so this is the forward model for our data, but we never, ever get to see h. Okay, we're going to try and learn h. So we'll only observe h through data. This is what we've been doing for the whole course, so hopefully not super surprising now. What that means is we're going to have yi, which is the data we observe. It's going to be some function h theta of xi plus some noise term. And here I'm going to assume the noise is Gaussian. Same setup we've done in a couple different ways. All right, so here I've charted x and y in some particular nice example where x is going to, just be some polynomial function. And indeed, there's the true function. And then we've gotten some noisy samples. These characters are really close to the line. These characters are, a little bit further away from the line. There's a little bit more error there. Okay. So what I want to point out, though, is that when you get a training set, every fresh data set is just a different set of points. Okay? And we're going to come back we're going to analyze what happens as we change those points in a bit. So we could judge our model based on exactly just the data we've seen. It turns out that's hard because we want to actually, the kind of guarantees that we can actually prove reliably are something that say, maybe we got a really bad training set. Maybe we just sampled one point again and again and again and ignored the rest of the function. That could be pretty bad. Just the same point again and again and again. So we kind of want to have this kind of randomness over all the training sets that we could have seen, and we hope that our function trains well, meaning it's got to kind of produce something that's close to this true set when it's fed different training sets. Okay, so is the model clear? So far we've thought of there being training sets fixed, but now we're kind of thinking about the training set itself is going to be a sample from some population. All right, ask me a question if unclear. All right, so let's imagine we produce 3 different samples of that data set. S1, S2, and S3. They're just different draws. Now you could imagine that they're drawn randomly if that makes you feel better. They could be drawn in some way, but right now they're just 3 different draws of the data set, okay? Now underneath is the same true function. So all the xi's are all the same. And indeed, in this idea, there's a hypothesis. There's a true relationship in the world between x and y. So this curve is the same on every one of the samples. But the samples are different. And they have different noise on each point, potentially. And the points themselves are different. So the x's and the eventual y's are going to change. But they're a draw of the same underlying set. So far good? Awesome. All right. So now, what we're going to think about in this lecture, which gets us to bias and variance and all that other good stuff, is how does the model change when we fit the same model class to each one? So we'll fit it to S1, independently fit it to S2, independently fit it to S3. This is kind of the mental model. And we'll want to see if the model should change. And so intuitively, it should be that on any one of these data sets, no matter which one you throw at our procedure, if it were the ideal procedure, it would just spit back exactly the true model. Okay? We'll see that that's not always the case, right? Some model classes will make systematic errors, and we'll try and capture those systematic errors. And that's what bias and variance are really going to be all about. Okay, so let's fit the simplest model. Let's just fit a line. Our function's quadratic. We're fitting a line. Intuitively, it should be too simple, right? There should be a curve. The line is incapable of representing the curve. So what happens? So what I've shown here is we took S1 and we fit a line, and boom, the line went off in some direction. And it has some errors on the points. I fit on S2, I again get this data set, and I fit a different line. And S3, get a different line. Okay? Now, the point of this, kind of schematically, is that this thing is kind of bouncing around a little bit on every different data set I give to it. It kind of fits a different line on each one of them. But also, it makes a lot of errors. Okay? So there's 2 different things going on. One is, if you think about this for a second, no matter which line I pick through these data sets, there's always going to be some amount of error, right? And if you actually compute it out, you can see that that error is going to be something related to the integral of that quadratic over the space. Does that make sense? No matter which line you draw, you're never going to draw a line that has a nice curve like it. Doesn't matter which one you draw, okay? You can sample all day long till you're blue in the face. That's one. Okay? So this is obvious even from the training data that we have. Now the fix here, hopefully, is clear. This is what we call a high bias situation. We're going to do the math in a second, but we're underfitting the model. Our model is just not expressive enough to capture the phenomenon we're after. We're after a quadratic thing, but we only have a linear thing, a linear model to go after it. Okay? So the fix is, well, let's add some degrees of freedom. Let's make our model more expressive. All right. So now we're going to fit a really high dimensional polynomial, right? We don't know what the true function is. We don't know what it is. So let's go and throw a true big function after it. So here, I think if you count, I think these are 9-degree polynomials. Maybe the notes actually only said 5, but these are, you can see how much they're oscillating. So again, on each set, I'll fit a polynomial here. I'll fit a polynomial here. I'll fit this polynomial here on each set independently. When I look at those sets, if you remember your Lagrange interpolation, right? If you have more degrees than you have points, you can fit every point I give you. So this has kind of the opposite problem. Here on the training set that I give you, I'm getting down to 0 error. In the last one, I was not getting 0 error on the train or the test error. This one, I'm fitting the training set perfectly, but somehow each time I give you a new sample, I get what looks like a completely unrecognizable function. And that would be very disturbing. For example, if I made a prediction here, I would get something that was in infinity, and here I would get something large, but here I would get something small. Does that make sense? If I took the same x value across each of them, my predictions are no longer stable because it's wiggling around in such a crazy extent. So far, so good? Cool. All right. So the curve changes a lot from one sample to the next. One sample here being an entire training set to the next. And here, this is an instance where the model is kind of comically too powerful. I wanted to fit a quadratic, but I had some huge, polynomial underneath the covers. right? So the fix that we'll talk about here is using an expressive class with lower variance. Now, this is the classical story, okay? This is what we're going to talk about for the next couple minutes. But I do want to point out that machine learning, as I said, and what we'll get to in the second half of the lecture, started training models that were actually larger than the data set. And so in the second half of the lecture, we're going to come back and revisit this idea through some more interesting ideas from the last 5-10 years and talk about how this evolved in the future, okay, to modern models. But the classical, you must know, anyone who passes through machine learning or stats needs to know, is high variance and overfit. Another way to say that is, what's likely to be on your test is the first part of what's going on, not the second part, which is basically me teaching you about what's going on in the last 5 years, okay? Because this is the classical bias variance decomposition. You should know what we're going to do. Okay. All right. Now, another way to think about it is the model is fitting noise, not signal. The true signal is this nice, smooth parabola, and it's fitting to all the little noise. And as a result, it's jumping around wildly, okay? We've done this in one dimension, but it's certainly true in higher dimensions as well. Higher dimensions even get worse because lines in higher dimensions are pretty expressive, as we've talked about. And so a higher dimensional line where you use too many dimensions, you can also get this kind of property where you figure out a line which almost perfectly fits all of your data, but it actually doesn't generalize well when you go to a test set. And to think about it, just to be really concrete, imagine I trained on S1 and then S2 was my test set. I would make huge errors using the function that I used on S1 on S2 and vice versa. Clear enough what the concepts are that we're looking for? All right, we're going to do some math. Keep these pictures in your head. All the math is basically just these pictures. If you understand the pictures, the math is just some kind of, plug and chug kind of stuff. All right. Now, the last case, of course, to fill it out is I get it just right. Now, just right doesn't mean it's perfect. That's all I want to get across on this slide. Just right means it has the fancy term for this that you'll hear machine learning people say. You should always ask them to define it because they don't think they know they can define it. It's a tough thing. Inductive bias. It's the right inductive bias. Sounds really professional when you say that. Just means it has a degree that matches the model. Okay? The degrees are free to match the model, more or less. So the fits are similar across samples and they stay close to the data. Okay? And sure, they make some errors. But those errors somehow are the errors that are in the data. If I gave you a really bad sample of training data, your model class shouldn't kind of be held accountable that it also fit a poor model. And so what we're going to try and do is disentangle these three sources of errors. What are errors when I come to test time? What are errors in terms of bias, which is how far I'm off, what the line is off, is what that term is going to be called. And the last one is that variance term, which is how much do I jump around effectively as I train the training set. And those are going to be the three terms in what comes out in the math we do next. Okay, so you've seen them kind of 1, 2, 3. All right. All right. Now, this is the classical picture. These are the three terms. We're going to derive them momentarily, which is that we're going to talk about more precisely what happens at test time, right? Because we're worried about generalization. I'm going to give you a formal model, but intuitively, you're going to pick a new point, however you want. That new point's going to have some error in it as well, because it's a point. And then we're going to try and understand, that's what's called the noise. And then we're going to look at these terms, how bias and variance trade off. And this is the canonical chart that you usually see, which says, as I increase the model complexity, the bias reduces, right? So we did it with lines and degrees, but canonically it'd be like more parameters, a more expressive function class. The hypothesis class is bigger, the number of functions you could fit. This thing goes down. But then after you get to some point, the variance, the ability to jump around and fit everything goes up. Okay? Okay. So far, so good? All right. Awesome. Okay. So what this looks like for polynomials, we already saw. We're going to expect this. These are all just what's written in the chart. You see what each one of those terms are. But let's see what the terms actually are and derive them. It'll make it more clear than looking at this. This chart is really for you to look back at when you go through and say, okay, I've seen now the mapping from the math to the charts, and I want to make sure that I test my understanding. That's when you should come back to this chart. Okay. By the way, you'll hear me use this phrase. I just want to point it out. Interpolation. This means something actually very precise to me. Interpolation means the ability to fit the training set with zero loss. Okay. So when you say that a function is interpolating, it means it can fit exactly those points. And if you've ever seen what are called interpolative methods, like if you know what a Chebyshev series is or something, doesn't matter if you don't. But if you've ever seen those methods, you take all the points exactly and then you weight the points. Okay? And it turns out, bizarrely enough, there exist large, deep networks that interpolate their training set and still generalize. which is something that you would think a high-dimensional polynomial shouldn't be able to do, right? If I give you a high-dimensional polynomial and exactly fit the points, it gets really weird and wiggly, right? And so you wouldn't expect that to happen. And there was a wonderful paper written by some friends. Actually, the senior author on that was one of my dear friends I was talking to this morning about unrelated things. I shouldn't embarrass him. He also does strongman competitions, which is actually the bulk of what we were talking about. But the other side of what we were talking about did actually have to do with the update to these papers, Rethinking Generalization, which are really interesting papers that show you things that you wouldn't think should happen. Super cool paper. Okay. Yeah, I'll probably embarrass the crap out of him. But yeah, Ben Rex his name. I just want to put it out there. So he's phenomenal. Any case, all right, we'll keep going from there. Okay. So the key is that once you get larger in polynomial space, this D gets bigger than D star. So I'm going to use this star notation to mean optimal. The optimal, like that's the right parameter class. Once you get bigger, the bias goes away intuitively in the classical picture because you have enough expressive power to fit the model. Below that, you're probably going to suffer bias. And then above that, you would expect that you get some amount of variance. And we're going to deal with that variance by regularization. So the idea is we don't know what D is. We don't know that it's a quadratic underneath the covers. And so we're eventually going to develop methods that regularize. They try something out. One second. They'll try something out to in a high dimensional class, and then they'll try and kind of smash down the complexity adaptively. And so they didn't know that there was quadratic data underneath, but they'll kind of fit to that data. Okay, that's the mental model of where we're going. Please go ahead. Sorry.
D is greater than D star.
Which one? Was completely gone.
Like this.
Oh, this is just for polynomials. Don't read too much into it. It's because you can always fit a low degree polynomial by zeroing out the higher order coefficients. Yeah. Wonderful question. Okay. I do want to point out before I do the math that I'm going to teach you this in regularization. Was there a question? Sorry. Oh, please.
I was going to ask, is it true that train error reflects bias and test error reflects variance?
Wonderful question. So the question is, does train error reflect bias? Is it captured in there? And does test error reflect the variance? It reflects a little bit more than variance because it also has noise. We're going to come to exactly what those terms are. And the test error will also have this bias squared component to it. So bias will leak into that as well there. You're right, too, to think about train error as primarily having something in bias of like, how poorly are you fitting your data? In practice, there could also be other errors that have to do with optimization, but assuming you got to the right model, then your intuitive understanding is absolutely perfect. Great job. Wonderful question. Are there others? We're going to see exactly that decomposition of the test error in the next 2-3 slides. Other questions? Awesome. Let's keep going. Oh, I wanted to make this point. I know I made it briefly. This kind of the story is easy in regression. The reason I'm going to show it in regression is because the math is really easy to see. It's like all simple derivations. Classification also has this problem, right? Where you have these high dimensional kinds of issues, right? Like we talked about this almost briefly before. You see how there's these kind of strange, weird islands that are there? This could be quite disturbing, right? If you just take your point here and wiggle it a little bit, you go from one class to the other, right? If I look at any of these regions, if there's a small little region there, it could be that is actually an island that is in, the red class versus the blue class. But probably we expect that the decision surface should be a little bit smoother, okay? And that's just intuition. But hopefully that makes sense. You would be surprised if you had a small amount of error in your features that led to a different class, for example, underneath the covers. So this all happens in classification. It just happens more abruptly. And the point is, it's about the model class that we're dealing with. Okay. All right. That was the intuitive piece. I hope it was intuitive. You see what the main characters are. Please go ahead. Yeah.
If you look at it a little bit and change it back, that's not really a good thing. But I mean, if there's like a very good model which is, also like with no variance, wouldn't that actually happen?
Awesome question. So the question is, are all little wiggles in changing class bad? And the answer is, of course not. Even on this model, which I claimed was good, a little wiggle does change potentially the thing if you're close to the decision surface. It will always be the case that some models come in. What I'm trying to get across here, and it's a great point, I didn't do a wonderful job on it, is if you have these things which are somehow discontinuous in the space, then the space, the featurization somehow doesn't quite capture the class. And so what's going on there is you have these little pockets or these little islands, and it can just be kind of overfitting. This is the analog of what you were seeing when you saw the function kind of wildly oscillate. And so we tend to think, hey, this may be a warning sign. But you're exactly right that this could actually just be the class boundary. That could also be the case. It just seems intuitively less likely. Great question. Others? Awesome. All right. Bias variance decomposition. So we're going to talk about this precise model of overfitting and underfitting now. And it's going to be just a very simple mathematical thought procedure. So let's walk through exactly how it works. So here's the thought procedure. We're going to fix a test point X. And really, I'm not going to be precise about how we pick X, but your reasoning shouldn't depend on X. You're not going to pick something specific about the function. You're not going to look at its decision surface or anything else. You're kind of picking a generic function X. Does that make sense? Okay. Then you're going to draw n training points, xi's and yi's. That's your SI that you had from before, the last slide. This was one sample of the training set. Then you're going to train a linear regressor or a hypothesis, whatever hypothesis you want. For this point of view, linear regressor is probably overkill. I should just cross that out. It doesn't really matter what we're going to do next. Okay? Oops. Who cares about this? You're going to train a hypothesis, H. Okay? Get that hypothesis on there. All right. Then you're going to draw a fresh sample at test time, X and Y. And you're going to check this. Okay? You're going to compute what is the model, Y at that point. And then you're going to measure this quantity, which has a fancy name. It's sometimes called statistical risk. But you're basically going to say, with the H that I've learned on the set, that's what this H of S notation means. So you've given me a training set, I fit a line or a quadratic or whatever my hypothesis class is. I'm going to use that to predict on the X that I selected at this test point, its Y value. And I'm going to suffer in the terminology, which is kind of a grim way to put it, but it is the tough terminology. I'm going to suffer a loss proportional to the square. That's the risk. Please. Great question. So where does the question is, why am we adding this Y error underneath the covers? And that Y error is something that we would observe on any point, right? So the mental model is that this is the way that data are created. And the test data is created in the same way as the train is created, that we would have that underneath the covers. We will guess that it's this value, and we'll come to exactly how that epsilon figures into our calculations in just 1 second. But it's just uniformity. Train and test are the same. Cool. All right. Now, what we're going to analyze as a procedure is actually quite complicated if you thought through the details of it, which is we're going to average over all the randomness that we did in this and try and analyze the quantities underneath the covers. Okay? This is different than the way we've been thinking where just one training set comes to us. We're going to think about all the training sets that we could have produced. So we have two sources of randomness. The draw of S, that means this step here where we draw n training points. Okay? So it's going to be drawn according to some random process. And then the draw of epsilon at the test point, which is this epsilon we just discussed. Okay? Clear enough? All right. Now, we talked about this already, but this is just to recap. Y is this true data point. H star, this is the true model. Remember in our quadratic, which came before? This was the fact that there existed a quadratic with exactly the right theta 1, theta 2, theta 0 that we had before, and we generated all the data. And we fit this model, H of S, on our training data S. Okay? This is what we're looking at. Now, the quantity we care about from that last thing is this expected value. This is the expected value over the epsilon error. This is the error that was introduced on the test point. And S, which was the draw, which produced this function. And we're going to try and decompose that error into 3 pieces. Please.
To assume that we have enough parameters in our points X to correctly predict Y.
Wonderful question.
This is like this universal function kind of presupposes that that's the case, right?
Wonderful question. So the question is, can we assume, or do we have to assume for this analysis, that H actually can get to a zero loss solution, that there exists an H which exactly fits Y? We don't have to assume that to get here. We'll see where we pay for that. If, for example, we're fitting H's that are too small, they're linear, and we wanted a quadratic, we should pay for that somewhere. And you're going to see one term that we pay for that in a little bit. There's also going to be a separate variance term, but there's nothing here that requires, like, we could pick a completely insane set of H's here. We could still analyze it. Yeah.
More like that the true data generating process uses like all the points in all the coordinates of X. Like we're assuming that
So I don't know about coordinates. So it's true. Okay, so one thing that you could think, which is not linked in my head, but just to make sure it's clear, is the data generating process is some function h star. You could say it's only reasonable that our h of s that we have down here contains h star. So a set of all h's that we could learn should contain h star. And that would be a fairly sensible thing to do, and in most setups we'll do it. But it's actually, strictly speaking, not necessary, because it could be that h is drawn from some other function class and we're representing it in a different way. And everything I'm going to say will also go through. We'll see exactly what assumptions I need to make. Basically, what I'm going to need to make is I'm going to need to be able to analyze how H performs on the training set, and I'm going to be able to analyze the error. And let's come back and talk about it after we walk through. But doesn't have to be an assumption that H star and H are related, or that even all of the coordinates of X. It could, for example, ignore some fraction of X, maybe the first two coordinates, and predict Y solely from that. H star is free to do kind of whatever it wants. It's true, I will say that intuitively though, although that's true, it's a weird thing to do to predict a model that can't possibly be in the class. I'm just saying there's no reason that you have to. Okay. All right. So there are two independent sources of randomness: the training set size and then epsilon. And why are they independent? Because of the way we set up the model. We did the sample, we took the points, and we added some independent noise. So they are going to be independent. And that's really what we're going to use here. Okay. H of S, it's worth saying, this is a crazy difficult random variable. Okay? Think about how complicated it is. It's the random variable that comes from, I sample an entire training set, and then I train a model on top of it. So I randomly sample points, and I train a model on top of it. For maybe a linear model, you could think what this is. You compute some inverse over the data you sampled, all the rest. You can compute that answer. It's called a fixed design problem. You can't actually go through that. But if you have some complicated neural net, whatever it is, this is actually a very complex variable of S. But we only need certain properties of it, and those are the ones to fixate on. We only need that we can take an expectation over it, that the expectation is well defined in a way that I'll make precise. The second thing is the test point. This is a very simple random variable by contrast. This is the one we've been dealing with for quite a bit. It's just that we're adding in some epsilon noise. Okay? Some zero mean epsilon noise. All right, so let's go through it. All right, so we're going to expand this function. Okay? This is just expanding the definition of y. And now we're going to expand the square. Oh, please.
Question in the previous slide at the end. So you said that h of s is like a very complicated function, but like s is like something which we are just like randomly sampling from the entire like set, and then that basically captures like a limited representation of the data. So shouldn't like h of s be like a similar function? Like why would it?
Yeah, so you're making a relative statement. It's a great question. So when I say it's complicated, the way that H is defined is as the result of a procedure which makes it difficult to analyze. And it's exactly the procedure you said. I've sampled some function S. I then taken that point, maybe it's 1 billion points that I have. I've run some very complicated SGD, LBFGS, whatever algorithm on it, and I've produced the function that's my final estimate. And my point is that H would be very difficult for you to write down without performing the example I just said and being able to compute, say, its expectation, its variance, all the rest of it. So I'm saying it's a complicated variable. In contrast, epsilon, just a normal random variable. We know almost everything about it by assumption. That was the contrast I was making. Please.
The difference between your test set and training set?
So epsilon is going to be, again, great question. So what is epsilon? Epsilon is going to be this character right here, which is the noise that's introduced on every point. So the way we set up our model is all data is generated according to this process. Both train and test are generated with this process. And that epsilon happens to be the epsilon that I picked for that test point. Yeah, wonderful question.
Why do you need this symmetry and not like epsilon? Why can't you just run inference without an error?
So you could, I mean, you could just set this to 0 if you wanted, but then you would have a less expressive model. But that's also the other bit that we've talked about here is you don't get rid of measurement error at test time, right? So the point that was like, what does epsilon actually capture? If you had something that captured absolutely every element of your domain, then it would be appropriate to set epsilon equal to 0. But if you have any of the settings that we've talked about, you have measurement error in a sensor, or you have some bit of little bias that's done, or some lag in the measurement, whatever it is, all of those things are kind of generally thrown into, there's some amount of measurement error or loss then. And that's why we set this up. And so having these two processes be the same and have the same amount of errors, you don't strictly speaking need to do it, but it certainly makes things a lot easier. But I would say the part that I would object to is the test data is also messy. It's not something that you want to do. And if you want to figure out what happens when epsilon goes to 0, just set the variance to 0 in the next thing. It will fall out pretty cleanly. Please.
You have something similar, like in this conception, like why do we need epsilon if like we have randomness found the training set? Does that not account for it? Is that not represented?
Yeah, wonderful question. So the question is, why do we have two sources of randomness here, and what are they doing? One is about selecting the points, the endpoints that we're going to train on. That is one bit of randomness that we're going to analyze. Those points are brought in, they have the X's and the Y's and all that data that's there, and then we're going to train on that point. The reason conceptually we want to then have a test error, which is at test time we've selected a new point, and that point also has errors. We want to be clear that there are things going on at train set and test set that are different. And that in fact, when we look across them, like we want to understand what the effects of those two errors are. Some of those errors, as we'll talk about in just 1 second, are intrinsic to the test set. There are some things that you just can't do better than because your test set has measurement error. That will fall out from the analysis we do here. But there's no way that the training set, it's not like we want the training set to be random. This is the model. The model is that the data is produced according to a random process, and that's what we're analyzing. So it's not something where we're saying, oh, we have some randomness, so we're good. It's just, this is the way we've modeled the universe. This is the standard model that we've talked about in the course. And this epsilon is to capture different sources of errors. Some of those errors are measurement time. You can think about maybe most cleanly as measurement at train set, and some of those are at test set. The test set randomness also buries this fact that by selecting a subset of points, that complicated training procedure that we're running could fit them. So imagine I had an extremely bad draw from S, just to think about why imagine epsilon is 0. If I just picked the same point again and again and again, I couldn't fit a line. Even the simplest model, right? I would just have that one point. So clearly something interesting has to happen inside X. I have to get enough data to be able to fit my model. So my point is, that's what's going on inside the training set underneath the covers. Great questions. Are there more? Please keep asking. All right. All right. So let's expand. So when we do this here, what we've done is we've substituted out Y, and we've looked at the squares. And when we look at the squares, we see two things. One is we see this term that comes out when we expand the squares as sigma squared. This is exactly that test error we were just talking about. This is the error that's intrinsic inside, I think it's the next one. This is the unavoidable error. So this is the error that's just in the data. If you collected the data with perfect measurement and accuracy, this could be 0. If it has any error in how you've measured it, or it's lagged, or whatever else you're measuring, this is just the error that's going to be completely unavoidable. And that's coming from this term here. The second error here, if you look, let's look at this. Oops. The last term is going to be 0. Okay. Now, why is the last term 0? That's because epsilon is mean 0, and it's independent from h of s. So the test error, when we do this decomposition, that error selection, whatever epsilon's value is, doesn't depend in any way on the training points. So those two are going to be 0, and that's going to cancel a cross term. And now we are looking at how far away is the true model from the one we train on an expected s. And we're going to decompose that further. Okay? So it's basically sigma squared, this noise, plus the expected prediction gap between h star and s. And so if you wanted to set sigma equal to 0, well, you would have this guy 0 and this guy 0 anyway. Okay? But this would be the new term that you would have. So now we're going to analyze this. Okay. All right. So we're going to define the long-run average prediction at x in the following way. We're going to think about, and this is what I said, we have one property of the random variable. H of average of x is going to be exactly this variable underneath the covers. And what it's going to do is it's going to sample some s, say that it's going to sample conceptually all the data sets of size 1000, and then it's going to fit the hypothesis. And we're going to worry about what that average hypothesis, averaged all the data sets, would actually be. Okay? This is I want to kind of emphasize, this is a very complicated random variable, but we just need to know that it exists. Okay? All right. So we're going to write h bar as h average here, and h of s of x in this way. And this is going to allow us to write this decomposition here inside the square. So we're going to take h star, and we're going to look at the long run average version, and we're going to look at h bar versus h of s. The reason we do that decomposition is this term here is going to be 0. Because this is the expected value of this guy under S. So this is equal to 0. This is just definitional. Okay. Now, that leaves us with the fairly famous set of terms, bias and variance. And these are related exactly to what we talked about before. This is a mathematically precise way to say if H bar is away from the long run average of what you would train, no matter which H you pick, whatever it is, there's just, no matter the amount of data you feed me, I'm going to have bias. That's what this term is, this bias squared. This term variance, this depends on the long run average and only the H of S I've picked, the data set I've picked. This is the part that's jumping around as I go from higher to higher degree polynomials. Okay? And so this basically says, this is how I can think about the errors. I look at this error and I have a noise term, a bias term, and a variance term. And all the errors break down. And this decomposition is quite powerful to think about how we're going to do this, because how can we reduce each one of them? Well, we motivated it in the setting where we had just polynomials, but now this applies to almost every prediction class. It's a large class of functions. So the bias is how far the average prediction is from the truth, and that's a property of the model class, but the sample that we pick from training doesn't enter in anywhere. That's just like, you can't fit a parabola with a line, okay? That's intuitively what's going on in that term. The variance is how much the prediction jumps around. Maybe you have a super expressive model, but it's not stable. And we're going to look at terms to reduce that variance later. So one approach would be, you could take a small model, fit it, if it fails, fit a larger model, and do that. The other is, and we'll talk about later, you could fit a large model and somehow regularize it, which means reduce its variance, as we'll see in a second, so that it doesn't jump around so much. And that should intuitively make the models better. Okay? And better means they generalize better at test time. That's what we care about. So this error goes down. Please.
The analysis we're doing is just for regressors, right?
Right. So the analysis that we did here is just for regressors. This is the standard presentation of it. What I asserted without proof is that effectively the same decomposition holds when you do things like classification or other models. And the reason I show this to you is this is like canon for machine learning. You will constantly hear people talk about, if you read papers or other things, bias variance decomposition or a bias variance result. And it basically is separating out the two effects. One effect that's based on the model class and one effect that's based on how the sample was for the data, right? And this kind of decomposition happens everywhere. We happen to do it just for regression. Just for L2 regression, with a normal added is all we did. Please.
Average is like the average of all the S, like is it the average of the S, or is it like the average of the entire?
Yeah. If you think about it, it makes your head hurt a little bit. So it is not the average of all the S necessarily. It should be if they're consistent, okay? But that's not necessarily the same. Here, what it formally is imagine S is a random variable that says a sample from this population that has 1 million points. It is the expected value over all the possible 1 million points that you could get and the weight of each one of those sets. It's a very complicated object. It is not the take all of the data and fit it. It's possible those estimates are the same, but not uniform. That's called consistency. Yeah.
Linear model and your data is like very quadratic.
Right.
It's super off. Like their averages are the same. You have like no bias, even if it's like super high there.
Yeah, so the variance that you get here is across training sets. So if your data were quadratic underneath the covers and you were fitting it with a linear model, then no matter what underneath, every time you sampled from that model, there would always be some bend in your data of the same shape, just with a little bit of noise. In that case, your long run average would be like some line that goes just through the model. You can actually see that it will actually be, if your model is ax squared bx plus c, it's actually going to be just the bx plus c term, okay? Plus a constant, which is called the offset, depending on how you do it. So that term right there is going to be the best you can do. And so you're always just going to fit that very, very simple line underneath the covers. The jumping around will happen if you have a model that's too expressive, where because the noise is coming, each different sample you get from S, it's picking a different iteration. And so this variance is going to be higher. That's what's going on. Please.
It's the average predictor like the best you can do. Could you not imagine a situation where a predictor that isn't the average predictor is actually very close to like H?
Yeah, so the question is, why is the average predictor kind of the best you could do, or is a good surrogate? Well, the best you can do, of course, is H star, right? So it's not the best you could do in that sense. What's going on here, though, is we're analyzing, if you gave me a model class and you trained that model class, what would you get? And so what you're proposing is a different model class. And in that model class, there's a new H star, or H bar, which may indeed be closer to H star over the expected value of all the places that it's going to be evaluated on this new text point. And that would be a good thing to do, but that's how the abstraction works. You give me the model class, we look at the long-running average. Now, if you say, I have a different procedure that I'd like to run to be able to create that model class, like I'm going to pick a different H as I train, that also is a different model class. That's called regularization. That's one example of regularization. We're going to see that exactly next.
The variance, but it could also reduce the bias.
It could have an effect. It could have an effect on the bias, but primarily it's designed to reduce the variance. Okay. It does have an effect. You'll see ridge regression, where actually you trade a small amount of additional bias usually for a large reduction in variance. That's the usual way the trade works. Like, I don't mean to be mysterious about it. That's usually what it is. You trade a little bit of bias for a big variance reduction. Okay. All right. Okay. All right. So we've gone over these pieces before. I'm going to go through them. All right. So decomposition hands us the next two topics that we're going to look at. The combined effect of bias and variance, this was an earlier wonderful point, can be measured empirically with a dev or a holdout set. What is a dev or a holdout set? Well, what I could do is I could have a training set, I could have a test set that I'm eventually going to test on, and I could have some kind of random additional sample of my data set that I use just for parameter tuning, fitting, testing fits, trying out procedures. That set is called a holdout or a dev set, and you can see that there. It's separate from training, and it can estimate the test error locally, okay? So you don't have to spoil your test set. Statistic-minded people are very worried about spoiling their test set, okay? So like one thing that you could worry about if you're a statistician is, oh my gosh, once you see the test set, all this information leaks through, and now you're going to be able to cheat in some interesting way, and then, validate the statistical sanctity of that set. We're going to come back and talk about, at least in one of the most major competitions in machine learning over a decade, that did not happen. Okay? That's called adaptive overfitting. But that's what statisticians are often worried about here. And it does happen, just not in this case. The variance is typically reduced by regularization. This is exactly what we just described, at the cost of a little extra bias. Okay? We'll talk about exactly what regularization is in a second. And we're going to come back to this modern picture. Okay. All right, so what is regularization? So we want to reduce variance in training to get a more robust model. Okay, so this is going to be the procedure that's going to design to reduce variance. We're going to allow it to put in a little bit of bias, potentially to get a more stable model, because our error is going to be a sum of those terms, and the win is going to be bias goes up by a smaller amount, then variance comes down. Then we would consider regularization a win. So the Bayesian view is what we're really doing is encoding prior knowledge. Some people find that helpful. Some people find this frequentist way I'm describing helpful. Oh, it's just a trade-off of errors. Or maybe I know something like, I know I'm fitting a line that isn't too steep, right? I know my line should be kind of flattish. That would be a prior distribution. That would say thetas, if I look at the size of the theta i's, they just shouldn't be too big on average. Okay? So it's general, it's used far beyond linear regression, like you use it in every industrial model in the world in some form or another. And the goal for the next slide is to show you how to use this in a couple of concrete places. Okay. Clear enough what the mechanism is? We have those three terms. We're going to try and get lower test error, hopefully by reducing variance by more than we increase bias. Squared. No. Okay. Let's look at least squares. This is going to be ridge regression. We're going to be able to derive an estimator here and see everything that happens underneath the covers. All right. Okay, so ridge regression, sorry to skip. Ridge regression here is your favorite least squares that you've done before. And then we add in this new term here, this new penalty term for some row that's going to be greater than 0. And this was the thing I was mentioning. Oh, theta, it's squares, it's not too big. We don't know exactly how big theta is because it's an unknown parameter that we're learning. We don't want to fix its value, but we know that it's kind of not too big. And if we start to make it really big, it's got to be worth it that it fits the data a lot better. Okay, is the intuition for what this formula is kind of roughly saying clear? We're going to derive kind of what happens as a result of adding this term. Please.
Why do we care about the size of the coefficients and not like the order?
Yeah, great question. So the thing is, why do we care about this size rather than the order? It turns out that regularization is one of those things that you can put all kinds of different penalties on it. You could ask that it's sparse. You can say, look, I only want to have a sparse set of coefficients, or I want to have something that's nearly sparse, or I want to look at the squares of the coefficients because I think the norm should be small, or I should look through some test statistic and do it as well. Those are all different modeling choices that you'll have. So there's no one that's right or wrong. The reason we're going to use this one is the math is super clean. It will boil down to exactly something we can see in least squares. And this is one of the more common things. Like if you go and download like a PyTorch model, one of the ways that you'll probably do regression or regularization is you may use something called dropout or you may use something called weight decay. Both of them can be actually interpreted as adding a form of L2 regression on the weights. One of them is model shrinking in weights actually induces exactly this behavior. And dropout, also a wonderful paper. I think Percy wrote that paper about how dropout and regularization are the same. Please.
Sure. Is the penalty term within the sum or outside?
Yeah, it's outside the sum. It would just change normalization, but yeah. All right, so if this is going to shrink theta toward the origin, so it just means we don't think it should be too big. It's kind of a soft penalty, okay? Now, if we set it to 0, this is plain ordinary least squares. If we set it really, really large, there's a value at which basically predicting 0 is kind of the best thing to do, right? Because if this thing is massive, as we get closer and closer to setting that to infinity, this one wants 0 and this one, and stop caring about the test error. So clearly my point is that there's some sweet spot for rho that's going to, give us good error. It's going to shrink that theta, and it's going to still respect some of the error that we have over here. Clear now? So this is just saying at 0, it's playing ordinary least squares, which has the issues we talked about. When it gets very large, then theta gets closer and closer to 0 to satisfy this penalty. All right, so a good balanced rho balances the two. The right ratio depends on the data. They're really hard to know up front. So we fit rho from data, and this is sometimes called hyperparameter optimization. We'll get to that if we have time at the end of this lecture. Effectively, what happens is you have some little dev set that you're developing on. You try various different models. You train on one set. You hold out. You test on another. And you see which row does better. Okay? And we'll talk about ways to do that in a way more parameter efficient way, compute efficient way, where you run fewer trials to bake off the different rows that you have. And we'll also see ways to do this in a more data efficient way, where you don't have to throw away a lot of your data to be able to have a holdout set. The latter one's called cross-validation. The first one is what this algorithm hyperband does. Okay? So this rho is a very strange parameter, how it affects things. All right. So why do we penalize? This is just illustrative in the least squares case, but it carries over to kind of the intuition on even more expensive models. So take X that lives in ND with N less than D, fewer samples and dimensions. Okay? So XTX here is not full rank. So for any theta we train and any V in the null space of X, this equation holds. That is, X times V is equal to 0. And so they give exactly the same predictions. So the question in the underdetermined case is, which of theta among all of these should we pick? And intuitively, there are infinitely many of these optimal thetas. We can pick any one of them. What we're going to pick here is, when we add this in, is we're going to pay if we have any additional component that's, something we don't need, that's perpendicular to what we care about. So any V that's in the space, that's in this null space, we're going to pay by V squared. Is this decomposition clear? If you take two vectors that are orthogonal, their least squares sums break apart like this. Okay? This is just the inner product expansion. Not clear, please ask me a question. But the point is that penalizing this implicitly without knowing the direction says shrink theta 0 a little bit, that's in the space I care about, but really penalize V, right? If you're doing an optimal procedure, gets nothing out of V, it doesn't change the prediction, it will kind of set that to 0. Does that make sense? So kind of is it clear why it's going to reduce the space of what we're after? Because V is going to go to 0. We're going to basically, everything that's in the null space, which is V, is going to get pressured to go to 0. Okay? All right. So another way to say this is that the penalty is trying to force us to pick what's called the minimum norm solution. So when we do those other methods of regularization, you could wonder, is setting the norm of the weights also doing a form of least squares regularization? Yeah, they all are. They're doing this sort of nice kind of smooth regularization to try and get out the tie. Okay? All right. So what happened there? When we did the solution, recall these solutions. If we make rho greater than 0, this is the equation for theta. Is it clear why? Let's look back to make sure. I don't know if I derived it properly. If we look, sorry to go back. Oops. If we look here, this character is nothing more than rho I rho, right? And so when I do the derivative, when I do this derivative, I get exactly back this least squares cost. Rho I. Okay. This is one of the reasons least squares is so nice with this ridge penalty, is that that rho falls immediately inside. How do I get that? Just take the derivative. Take the derivative, you're going to get a theta that's there, so it's going to be theta rho I, right? Boom, you move it across. If not clear, I'm happy to take 2 seconds to derive it. Okay. No. All right. So now when the inverse exists, if lambda 1, lambda 2, and lambda d are all the eigenvalues of the dimensions that we have, the eigenvalues of this thing are all shifted by a constant rho. This is the bias, right? We're shifting this thing in some direction. But the advantage we get is, now, this is full rank. Why doesn't one of these things end up equaling 0 if rho is non-zero? What property are we using? We're using the fact that XTX is positive semi-definite, right? And so what that means is all of these lambda i's, great point, all these lambda i's are greater than or equal to 0. And so when this thing can't introduce some extra element of the null space because this is a non-negative number plus a strictly positive number, that means this is going to be strictly positive. Cool. All right. All right, if you care, I derived it and put it in the appendix. The pseudo-inverse, what happens there, the Penrose pseudo-inverse, if you care what that is, that's another procedure to solve this equation. It also is a form of regularization. What it tries to pick is a minimum norm solution, which is sort of similar to what we're doing here. Okay. All right. Now, the variance of theta hat involves eigenvalues that shrink from this 1 by lambda I to roughly this expression in the ridge. And so the point that I'm making here is a small value here has huge variance, okay? So it's not just a problem, by the way, if lambda I is exactly 0, but imagine I have a very, very small, weak eigenvalue. I have lambda I 10 to the minus 5, 10 to the minus 6. What happens along that direction? That means huge changes, right, in the eigenbasis there do not change the error very much. So the worst case of this is when it's 0. When it's 0, the entire subspace does not change. But if it's really small, lambda I, and I take the corresponding eigenvector, any change on that direction doesn't really change the loss by very much. And when I'm optimizing, this can create a numerical instability. Here, by adding this, it bounds me away from 0, and so everything is all the eigenvalues are kind of large enough. This intuitively means that I'm going to get a better, more well-behaved optimization and a better model with lower variance. Because this is really where I pay for the variance, right, in the model. Is that clear? Please ask me a question if not. Okay. So this behavior, just to be clear, lowers the variance even when XTX is full rank. Why does that happen? What is the variance a function of here? If you have eigenvalues that are all the same in case 1, and in the other case you have a really large eigenvalue and a really small eigenvalue, which one is going to have proportionally a higher or lower variance, you think? The second one, where you have this wide spread, it's going to be poorly conditioned, potentially. Okay? If you start to make them more homogeneous and shrink back down in absolute values, close to 0, you're just going to have less variance. Remember how you compute the expected value of a random variable times a matrix, and you get out the covariance, right? It's exactly that computation. Okay. You guys are doing great. Questions? All right. So the point is, this is what I mean. I hopefully made this precise in math that you can go back and check or take a look at and make sure you evolve, which is that the trade-off here is a little bit of bias for a lot of variance reduction. That's when it's going to work, okay? We're going to get a little bit of bias. We're going to take something that's like 10 to the minus 3 and set it up by a small amount to say, 0.1 instead. But that's going to cause a massive reduction in variance because that model was really nearly singular. It was really close to having this property that, there was a whole subspace of solutions. And so theta wasn't well defined. And that's the trade-off we're making. Okay? Cool. Please.
Yeah, so I'm trying to get this intuition for this thing. So a very norm, for this condition, that is basically because our theta are very close to 0 and then our subset we made sure to the factor there. So, I'm just trying to create an intuition of why do small thetas have that condition where a little bit of bias change causes the margin in the.
So one question, it's a good question. So one bit here is if I imagine that XTX, because this is the way so the first point is when I actually compute this quantity, scroll back. When I actually compute this quantity here, right? If I look at what are the eigenvalues of this quantity, they are going to be lambda I plus rho, right? This thing here is going to be lambda I plus rho, but then I invert it. Okay? So you're going to have that little piece that happens there. When I have that inversion, if I have lambda I really, really small, then that's going to send a small change in XTX very far away. Right? Because if it's 1 to the minus 10 or whatever, then I'm going to multiply that by 10 to the 10 when I actually go to find theta. So a tiny change over here is causing a huge change over there. Okay? You can think about it as conditioning. You can think about it as kind of whatever you'd want. But that's the fundamental issue, is that when these things get small, this equation becomes unstable. When I add in a little bit of value here, a small addition changes the inverse by quite a bit, right? That's the asymmetry. If I take something that's 10 to the minus 10 and I add to it 0.1, it's 0.1 plus 10 to the minus 10. It's really 0.1. So now some unit of label here that I get from XTX, that's actually shooting back through here and only contributing a factor of 10 instead of 10 to the 10, which is a huge win. Now, the reason that lambda also comes in is when I modify it in this way, I'm also modifying X. So yeah, all good. Cool. Awesome.
Previously, I've seen rho written with an epsilon, where epsilon is 1 to the, or 10 to the negative 5, for example. But with this, you would set rho to something non-trivial.
Yeah. So this is a great question. So I believe I was actually going for a while with Andre a little while ago. I believe in the lore, it's called the Karpathy constant, which is 4e to the minus 3 or something. So this is a joke, but basically there were a bunch of these values that people heuristically set to have good regularization performance. Part of those are set, by the way, for a different reason, which is that when you do, so those are not for least squares, but traditionally what they're set, that's a step size rule for Adam. But the traditional way that these things are set is that you have other numeric concerns. So for the same reasons we were just discussing, if you have an unstable linear system and that is the condition number is really high, little changes are going to change theta kind of on the output. If you're doing that in FP32, if anyone knows what that is, the format that you have a whole bunch of bits for precision, maybe that will be okay. As you go down in machine learning, we use lower and lower bits of precision. So numerical precision is FP64. That's what a numericist cares about. But we may train in FP8. Okay? That means we only have 8 bits of precision. 3 plus 5 is usually the way you do it. Doesn't really matter. The point is fewer. And so then those instabilities really compound. And so those numbers are picked so that you don't have numerical precision errors and also that you get this little bit of bias. And weirdly, machine learning has gone to lots of sloppy values thrown at a problem rather than really precise values. So if you went to a statistician and used the R package, they would really care about getting all of the bits of precision and they would be very careful about how the regularizers were set. Trevor Hasty has a wonderful set of papers about what's called the lasso path, which is instead of L2, you use L1. And it's exactly what happens to the model. And they know exactly how to compute every detail. Machine learning, we don't really care. If I'm honest, we're just sounds good. I'm going to show you in 1 second, here are other ways to regularize your models. Randomly zero out things while you're running. Take your data and screw with it. That's data augmentation. Take the data as it runs and say, those numbers got too big and divide them. That's layer norm. Literally, this is the stuff we do. You just look at the data and you're it looks bad. Fix it. And these are the things that basically discourage the model from just fitting too much to one point. So if all this discussion was lost on you of like, well, how are we getting to test and all the errors? The most engineer intuition you can get is what you're trying to prevent is the model from fitting into the noise, fitting those things that don't matter. So you want your model, you make your model more robust by doing nasty things to it. Okay. And maybe they'll never forgive us when our AI overloads come. Like we didn't want to have dropout. We didn't want you to do, it used to be called optimal brain damage, which is a old paper. But like we didn't want you to do that to us, but we did because we thought it made them more robust. Okay. So the point is all of these you can actually formally analyze in the same framework that I gave you earlier. If you go and read the papers, they all do bias variance decomposition and they prove all these. I have a paper on data augmentation. Proves if you do a particular set of augmentations, you take the image, you rotate it a little bit, didn't change from a cat, right? If I take a picture of a cat and I rotate it a little bit, still a cat. I zoom in a little bit, still a cat. But the model may have picked up on noise. And so by doing those augmentations, I made it more robust. That's also a form of regularization. Please.
Standard intuition for picking rho, because I was just thinking like if the y values are much higher than x values or something.
Awesome question. Yeah. So the question is, what is the intuition about picking rho? There are some rules of thumb. Most of them, I would say, are not all that useful because what you want is you want them to all be the same scale. In 2 weeks, so you get a well-deserved break from me next week, but in 2 weeks I could come back and I'm going to tell you about how to standardize your data and whiten your data, and that will deal with the fact when your x's and y's actually have very different scales. We'll talk about exactly that problem and how that fits into a class of models which are unsupervised. But that's kind of what you do. The reason you pick these, it really does come down to trial and error. Like you really do try out multiple values and see how well they generalize. The existence of the dev set is much more trusted by engineers than any amount of math in this space. Please.
When we were doing the first regularization thingy, we had like the LP norm where P is equal to 2. Do we ever do instances where P is less than 1?
Great, wonderful question. So the question is do we use, those are not strictly norms, so do we ever use fractional norms or things below 1? Traditionally in machine learning, you'll use the 1 norm because it's convex. That's underneath the covers. You don't use the 0 norm, which is the one you want, which says, what are the support, right? Underneath there's like sparse recovery was the hotness in machine learning 15 years ago. So every form of sparse recovery has been beaten to death in some way in some annals paper. Okay. So it's all there. And so a lot of those things called gauges, all those things are done. Modern machine learning models don't care about what's called certificates. They don't care about getting the right X. So that's why in some ways the story that I really am dying to tell you is this is what I've told you right now is classical stats. You could have gotten this lecture, maybe higher quality from the stats department 15, 20 years ago. What I'm going to try and tell you and what happens next is what did we learn when we started to build these bigger models and what's on the other side? Because there's a couple of ways that this story is mathematically correct. Everything I've told you is correct, but there's a couple of things that it omits. And that's what I'm most interested to tell you about. Yeah. Cool. Awesome. All right. I'm going to skip over this Bayesian thing. This is another way to say that I can motivate that theta comes from a Bayesian distribution. And this would be one of those ways to pick, what is the ratio between them? So they are in the notes. But I really want to tell you the modern stuff because I genuinely love this stuff. All right. Okay, so the surprise of modern machine learning. So the classical bias variance story tells you beyond some complexity, the test error must rise, right? That was the picture I showed you, okay? A high degree polynomial that interpolates 15 points should be a complete disaster. You have a model that's extremely powerful, you're fitting fewer points, something bad is going to happen, okay? Now it turns out, and this is pretty interesting, we used to train models, we still do in some cases, train models that have many more parameters than their training points. They interpolate the training set perfectly. They exactly memorize it. But they also generalize. In some cases, generalize better than any model we know. Okay? So what the heck is going on here? So for much of the last decade, this puzzle for practitioners was not how do we avoid overfitting, like I told you, but why aren't we overfitting? That was the crazy thing. We were warned by our statistical priests and priestesses that bad things would happen if we ventured into this dark, woolly land. And then we started training big models and everything got awesome. That's kind of as you can tell which side of the debate I'm on, but that's kind of how it worked. Like GPT does not care about your least squares regularization. Anyway, it does do regularization stuff under the covers, right? It does do stuff. So that's not true. Okay. There's a wonderful paper by Misha and friends. Misha Belkin is the first author. And they showed, roughly speaking, that the following bizarre thing happens in a case called kernels, which we'll learn about later, but you don't need to know. There's the particular things. Where in the classical regime, you had this issue where the training set, the test error, indeed goes up. So model capacity on the x-axis, test error on the y-axis, and this is the regime we've been talking about. But it turns out, in a totally bizarre twist, that over into some regime where you're massively over-parameterized and past this threshold, the test error actually starts going down again. We're going to talk about this in 1 second. Now, you have only been thinking about bias and variance for probably about 25 minutes or an hour, whatever it's been in the class. If you've been thinking about this for 20 years, you're like, oh my God, what are these maniacs talking about? But Misha is brilliant. So when I read this paper, I was like, awesome. Now we understand. Misha wrote a bunch of awesome papers. I really love Misha. Anyway, so this is a classical regime, okay? So here you have this variance explosion, and then all of a sudden, it starts going down. So this phenomenon is called double descent. And the idea is that there are many zero loss solutions, and optimizers, when they're in this regime over here, they'll actually be able to pick out a smooth one. And so think back to the picture where you had those polynomials wiggling. Effectively what it's saying is if I had a massively overdetermined polynomial, and I gave it enough data, and I regularized it, I let it kind of regular itself, it would come up with a zero solution that actually generalized. That is a wild statement, but turns out to be true in neural nets and provable in some things. Okay. All right. So now, does that make sense? So I just wanted to tell you, like, this is, to me, one of the crazy things. We tell you train and test error matters, and it does. This whole picture is there. But it turns out that most of the progress from the last decade was jumping over this line and trying things that we shouldn't have tried. I don't know what you should take from that, except for that I think it's awesome. Okay? And it's like phenomenal. Things started to work. Things didn't work, then they started to work. Yeah. Let me tell you one other one. So a separate worry that you have if you've taken a stats class and you're well versed in it, and it's an interesting worry is, and by the way, this is a real worry. So for example, there's a guy at Stanford, John Ioannidis, if you know who John is. John, one of John's great contributions is he told the FDA, you should make people register your drug trials in advance. You try a drug, you should tell me what it does in advance, and then I'll come back. And they were very worried, if you've ever heard about what's called p-hacking or other things like this, where you try and torture your data into getting to your conclusions. And they had a whole bunch of things where they basically showed that by registering their trials in advance, drugs got safer. Monstrous contribution. Every worry to believe that something like that could go on in machine learning, right? You show us the test sets, you give us a benchmark, we all hammer on it collectively, and secretly we're taking bits from the test set and leaking them back into our setup in a way that not even we understand. Is the concern clear? All right. So, are they overfitting across papers? And another way to say it is, do the same good models stay good? Okay, that's what we'd be worried about. We'd be worried we tried all this fun stuff out, and then it turned out that one artifact of this data set called ImageNet, which Feifei created, was leading us in the wrong direction. We thought model A was better than model B, but actually it was an artifact of the data set, and we had been wrong the whole time. All right. So Ben, that's Ben. Ben and Ludwig works here too. Schmidt, that's Ludwig. And the other ones are great too, but they don't work here. Anyway, so I didn't talk to them today. Anyway, so built an image set that they rebuilt the entire set by hand. They went back, this is 10 years later, and built it and paid for it and did it and scraped it and cleaned it and tried to replicate exactly the set just on different images. And it was hard because imaging technology changed a lot in 10 years. What images people were changing were there. A lot changed. Here are the results. Awesome. This is the original thing. This is the original ImageNet accuracy. This is the new test set accuracy. If everything were perfect, you would expect it to live here. Something more interesting happened. All the models dropped by almost the same amount. And in fact, if you notice, since they're in a linear order, they didn't change ranking. So in a very strange way, and you have to understand, ImageNet was so popular that you had people getting banned at companies for cheating, for trying to download bits of the service, like major companies. You had entire labs funding based on how they were doing at various points in this competition. You had a wild competition to try and climb to the top of this leaderboard, where anyone who was doing computer vision effectively was testing, or large people were testing on ImageNet. And in spite of all that effort, a constant loss. And by the way, this constant loss is not mysterious either for another reason, which will come out. I was talking to Ben about it today. This fact that they drop is just basically because you have two different tests in the way that you've constructed them in weights. But the fact that their relative orders stay the same mean that also overfitting is a little bit overblown in this situation. Fascinating stuff. Okay? You could really worry about it. So does this mean that you can do whatever you want to your data? No. But it does mean that something more robust is going on in these models than we otherwise understood. Super interesting paper. Okay. Yeah, it was exactly 11 points. Not that 11 points is significant. Okay. All right. All right, so I'm going to skip through this. We talked about these two things. We talked about double descent, and we talked about robustness. Okay? So double descent was this idea that beyond the interpolation threshold, implicit bias from the optimizer plays a role, and that the explicit regularization you used to do, and actually it picks out a smooth model. The implicit bias I didn't cover exactly, but you could even see it in least squares. If you picked a least squares optimizer like Penrose inverse, or you ran with SGD with a little bit of weighting, you can see that you'll select something interesting. The robustness is also interesting. Even when generalization works in distribution, this modest shift costs, tens of accuracy points, but it still generalizes. That's the interesting part. It still generalizes even when you do these adaptive things that you think should lead to overfitting. Wild to me. All right. So my point is here, this is the thing I care about for you. You may want to think that machine learning is like this giant solved space. It is not. There's so much stuff we just don't know. 2018 was a while ago, but it wasn't like, 100 years ago. We still don't know these basic elements of how the world works, and they're coming out again and again and changing how we think about it. It's just a very exciting time in the field. All right. So the last 5 or so minutes, I'm just going to tell you one of these two things. I'm going to tell you what cross-validation is, and then I'm going to tell you what successive halving or hyperband is, because I think it's genuinely useful. All right. So cross-validation is basically solving the following problem. Your test set is sacred. Every time you peek at it, you could leak information and inflate an estimate of how good you're doing, how well you're doing on the test set. You do typically want to have a dev set where you pick these hyperparameters. And the question is, how much data should you put in the dev set? How much should you put in the test set to ultimately get confidence? And how much should you keep in the training set? And what we found over the years is we want to cram as much as we can in the training set because that seems to lead to better models. But that's the fundamental trade-off that we're worried about. So here's the basic idea. So let's say that you train on a set, you have the dev set, and you have a set of models. For each candidate, you train a model D, and you score on D, and you pick the model with the best dev score. Okay? If you do that, you can pick a pretty good model. Now, why don't you pick on the train set? This is the only key question I care about. Why don't you train a model on the train set and use the best train set as your potential value to pick one of these hyperparameters? Exactly right. You could pick, and the train set for the most expressive model, as we talked about, could be 0. Could go exactly to the bottom. So you have this other set that was sampled in an interesting way, and that allows you to get around it. Now, what cross-validation does is it says you want to be more data efficient. So it says instead of taking the entire train set and splitting an entire dev set, you split it into small pieces. Okay? This is a classical statistical thing. You may have seen this before. You split it into small pieces. You say you have 5 pieces. You train on 4 to predict the 5th. And that is enough of a mix-up that you're not going to then pick the most, expressive class because you're going to have this generalization and hold out to one piece of it. But I'm going to tell you about the compute efficient thing in just 5 minutes. Okay? Oops. Sorry for the scanning. All right. All right. So here's the idea. Okay. So this is a meet. He's at CMU. Jameson's, he's at Washington. So the core idea here is we're going to try and figure out from the models, we're going to try and run various different regularization parameters, say the rows. We're going to pick all the different rows and we're going to run them. And the idea is we're going to do the following. We're going to run all candidate models for a small number of steps. So we're going to grid our rows into small values. Row 1, row 2, row 3. Just try them, maybe at different octaves, whatever you like. We're going to score them all, and we're going to drop the worst half. Then we're going to run the survivors for twice as many steps. Okay? And we're going to repeat this until one model remains. Right, so let's see it in action. So each round is going to use roughly the same amount of total compute, but better models are going to receive exponentially more of it. Every round, better models are getting more and more data. Okay? So here's how it works. So we run the first set. We have these different configurations, A through H. And here, we're basically picking the smallest scores. And so when we pick the smallest scores, A wins, C wins, E wins, G wins, in the sense that they are in the top half, okay, of models. Then we run them. But we run them for twice as long. So A is getting actually 3 times as much compute as B. So we're devoting more resources to the things that we think are promising. When we run again, we see here that after the second half, A and C are scoring better than E and G. And so we keep them. We continue to run. And we continue to run. Clear enough how it works? Please. There's no need to sample. Here what we're doing is we are just running them all in parallel. There's no sampling going on whatsoever. Here, yeah, this is just underneath the covers in this abstraction. They're just running for however long goes underneath the covers. This is just about saving compute. So what's going on here is, let's say that we're going to have to fit some big model, and that model is going to take 2 days to run. We have 8 configurations of that model. So we could either rate 16 compute days, or we could try and figure out which one are we going to run faster. No, you continue. You can continue. Yeah, so each one of these continues. As you notice, the scores are going down monotonically. You got this exactly right. Hopefully this is clear. What I've done is, so all the compute basically that went into these characters in the final analysis is wasted, but a large fraction, you compute the exact fraction, went into the model that was eventually the winner, which I can then use to continue. Okay? So this very simple idea, by the way, did a huge, huge service, because you could do very complicated things in tuning, but that simple trick is one that I use kind of all the time. Very simple to implement, has very nice properties, and actually it has a bunch of analysis that says, if you have certain properties on the scores, this is about the optimal thing to do. And there were very complicated procedures that were proposed. I've listed a couple here. Some are quite good, but this tuning problem is a real problem. Okay, so what do we talk about here? I'm just going to get to the thing. So we talked about a couple things. We talked about overfit versus underfit. We learn how the learn function changes when we redraw the training data. This was a change from what we had talked about before. Previously, we had talked about there is a training set, and then we wanted to understand and analyze. Now we're talking about how the training set itself was sampled so that we could talk about the model class. What would happen what we expect to happen for a model on a new data source. We then saw those pictures and we turned them into bias variance. We decomposed into 3 terms. The noise, which was intrinsic in the test set. The bias squared, that was the line that we talked about. And variance, how much it jumped around from training set to training set, how kind of stable things were. We then to deal with variance, we added some regularization. We went through fairly quickly ridge regression in detail. And what ridge regression showed us was we could hopefully add a little bit of bias to reduce variance by quite a bit. And that was a general thing of regularization. And I made the point there that there are lots of ways to regularize models in modern parlance. And that this idea really that you should take is anything that prevents us from kind of overfitting to a point or trusting our data too much usually has some interpretation as regularization. I couldn't help myself. I don't think you have to know this for the course, but I don't care. I wanted to tell you. Modern models have this twist that past the U-curve that I showed you, the classical kind of bias variance trade-off curve that I show you, lives this other regime. And that's where most of the models that you probably use right now live. They live in that over-parameterized regime, or in this regime where, as you said, you have huge models relative to the amount of data that's there. We talked about double descent, which was that regime, and why robustness matters a little bit. And then this idea about adaptive overfitting. That is, being able to take a new data set and, apply it in the world. This is a very strong form of generalization. Somehow this still held up, even when we were benchmarking. And then we talked a little bit briefly about model selection. With that, thank you so much. Have a great rest of your week. Appreciate your time.